in the last part, we did a very detailed analysis on why these two proof obligations wouldn't actually discharge. And the very reason was we ended up having some contradiction to prove, meaning false as the goal. And we knew that the cause of the problem was the traffic lights on the island side and the traffic light on the mainland side, they might just be both turned green. And we actually show you how it is possible for both traffic light to be turned green using this example trace over here. You can see in the very final states, both lights are having their values green. And one more detail to recall, which is also very important, as we did before. We got two sequences over here for the proof obligation. Let's talk about them one by one very quickly as a recap. The first one over here is about invariant number 4 for model 2. Invariant number 4 is about if the island traffic light is green, that means the opposite traffic should be 0. So if the island traffic light is actually green, that means the opposite traffic over here should be 0. However, it seems to be possible, seems to be allowed by our current model that M out may just be able to go through because the traffic light over here is actually green. In that case, we'll get A plus 1. A plus 1 cannot be 0 as the opposite traffic. And symmetrically, when we talk about maintaining or preserving the invariant number 3 over here, which is about the mainland traffic light to be green. In that case, we are expecting the opposite traffic C to be 0. So we are saying that in order for this to be green, we're expecting the opposite traffic over here to be 0. However, for our current model, it actually allows the traffic light over here, ILTL, to be green such that we can have IL out to be enabled, in which case we're going to get C plus 1. And C plus 1 cannot be 0. In that case, we got another contradiction. Right? So these are the two very important points that we mentioned in the last part. You want to make sure you really understand why we actually got such contradiction, which will force us to really look back to our model and make some fixes. So that's really the story. Okay, let's finish the other half. We now identify what the problem is. Let's now fix the problem. How can we fix it? Let's now go back to the slides. So what we can do is we can impose some additional constraint to really help us, because as soon as we add some invariants, we will be able to have some extra hypothesis when we formulate the sequence for the invariant preservation. You will see that. And what should we do in the extra invariants? Since our main concern is the two traffic lights on the mainland and also on the island may be turned green at the same time. What we want to do is similar to how we impose the safety constraint about the bridge being one way. If the bridge is one way, that means either A is equal to 0 or C is equal to 0. So now what should we do about the traffic light? We can do either of the lights should be red. That's a very similar constraint. So that's something maybe I wouldn't let you do the exercise. I'll just tell you directly. But you should really think about the way we derive this safety constraint over here is similar to how we came up with the one-way bridge as before, right? The one-way bridge was really about either A is equal to 0 or C is equal to 0 either way. So we're doing something similar. Either this traffic light is red or this traffic light is red. Similar pattern. Having this new invariance over here, now we got invariant number 5, right? You can see we used to have only 4. So now we got 5. So what the consequence of this is, we're now going to get some extra hypothesis in every sequence for the invariant preservation, if you think about it. And by coincidence, this new invariant over here about the two traffic lights cannot be green at the same time is really consistent with our existing requirements number 3, which is about the bridge being one way or the other, but not both. That's one way to think about where this invariant really came from. It doesn't really come from nowhere. Another way to think about this invariant, of course, is based on our detailed analysis from before, based on the contradiction that we actually resulted in by doing the sequence proof. So this is a really important process to really go through, meaning that whenever we construct our model, it cannot be just right for the first time. It has to go through some revision process, either by elaborating on the requirements or maybe by analyzing the felt sequence. Either way, we have seen just both. So what will be the consequence of having this new invariance? Apparently, it is going to impact the generated sequence for proof obligation related to invariant preservation. Let's see the two cases of the consequence, and then we're going to look at one by one. The case number 1, it will be about the original 6 times 4. Remember, we still have 6 events, but later on we're going to split some of them into 2 events, but we'll see that later. For now, we still have the 6 events that as we talked about before. And we got a 4 original invariants, meaning that invariant 1 to invariant 4. And for those of them, we know that these 2 failed to be proved, these 2. But with the new invariance number 5 over here that we just introduced over here, we can add this as an extra hypothesis in the sequence. Does that mean the 2 sequence will be provable now? That's something we'd like to find out very soon. And case number 2 is really about, since now we got an extra invariance, which is invariant number 5. So that's exactly what is times 1 over here. And we still got our 6 events. So that means there will be 6 additional invariant preservation sequence that we have to generate and prove. And we're going to look at 2 of them as well. But of course, for the proof themselves, I'll assign them as exercises for you. They should be rather straightforward to really discharge. Let's now revisit these 2 sequences in case number 1. And to make it easy for you, let's see, this will be the updated sequence that should be generated, but let's take a look at exactly what's being added. So this sequence is largely similar to what used to fail on us. This will be what used to fail. You can definitely look on your notes. And with a sharp eye, you can actually see that the only thing that's been changed is about the extra invariance number 5 that we introduced as the extra hypothesis. Right, let me write it down. Let me highlight it. You can see this is the new invariant. Let me make it thicker. This is the new invariance that we just introduced over here. Right? And remember, according to the rule for the proof obligation for invariant preservation, the concrete invariant should appear, the pre-state version should appear as the hypothesis. Since we have added one, so that's why there should be one extra hypothesis. And similarly, for the other proof obligation, I'll leave that to you as an exercise to specify it and later on to prove it. But I'll definitely show you the proof about this. So now the question naturally is, with this extra hypothesis, are we able to prove that sequence that used to fail for our first attempt? Especially with the extra hypothesis maybe adding over here, are we able to prove it now? The answer would be yes, but we need to see why. Okay, let's now go back. You should really understand. So I think this week's challenge would be, we actually got many more pieces of the model and for the refinement that should be put together. You want to know exactly where we are. Don't get lost. All right, so let's now take a look at the proof. And remember, this is the sequence where we were before, and this is exactly the sequence that we actually analyzed before. And we have done a good job, because now, after adding this hypothesis of invariant number 5, I claim that we will be able to prove it. Let's see exactly how. But before that, let me show to you about the updated proof. In the updated proof, you should just notice that we have added invariant number 5 in almost every sequence. Okay, maybe I'll make it a little bit thinner. So you can see this is invariant number 5 that's been added as an extra hypothesis. This is also the extra hypothesis. And the structure for the proof is really identical as before. So if you want to redo the proof, feel free. But for now, I just want to walk you through what's really the updates. Okay, this will be the extra hypothesis, the extra hypothesis, the extra hypothesis. What used to prove as the branch over here doesn't really get impacted. And extra hypothesis, and extra hypothesis, and finally, this will be the original unprovable sequence amended with an extra hypothesis over here. And I claim that this is now provable. Why don't we take a look to see why it is provable? Okay, let's now write down the proof together. This one should be rather straightforward. Before I start writing, I would like to offer you a chance if you want to do the exercise on your own. You may also want to consider these 3 inference rules that might be useful for you to prove the sequence over here that used to be unprovable in our first attempt. But now, with the help of the extra invariant number 5 as a new hypothesis, you should be able to discharge the sequence. Okay, you can now pause the video. Alright, assuming that you have some solution or proof on your piece of paper, let's now compare your answer with mine. And it would be reasonable to actually use this new hypothesis that we introduced as the new invariance, right, over here. And apparently this is disjunctive hypothesis. Right? You can see there's a disjunction over here. Let's identify that right away. And when we got disjunctive hypothesis, what rule can we use? Apparently, we can use ORL. And the rule says that if you got a disjunctive hypothesis to the left of the turnstile, you can split the sequence to prove into two independent sequence to prove instead. And one would have one disjunct, and the other one has the other disjunct, right? The left and the right, the left and the right over here. Right, let's apply that. So we're going to apply ORL over here, and it's going to split the sequence into two. Let me draw the box first. This will be, let me make it slightly bigger. This will be one of them, and this will be the other one. And it could be a little bit tedious over here to really copy all the hypotheses, but there's no way around. But let's not do it. I'll do it together with you. What we're going to do is we're going to copy all this hypothesis, but for this one here, we're going to copy only one of the disjuncts, either the left or the right. So we have green not equal to red. MLTL equals green. And let's say for this one we get a left disjunct. MLTL equals red. And one more, ILTL equals green. ILTL equals green. And then turnstile, and I'll just put 1 equals 0 over here. Right? Still readable. What about the next one? The next one will be mostly the same, except that we're going to choose the right disjunct as the hypothesis instead. So it's going to be green not equal to red. MLTL equals green, and also the right disjunct. ILTL equals red, and then ILTL equals green. And finally, turnstile 1 equals 0. So we're going to discharge this sequence first, and then we're going to do this one independently. What can we do with this? Well, you can see we got nice equalities over here. So here, there might be alternative to the proof. I'll leave the exercise to you, but for me, I'm going to choose this one over here. This will be the left-hand side. This will be the right-hand side. Okay, let me identify that. The left and the right over here. And do we have any other occurrences for the left? Indeed, we have one over here. You can try instead identify this as the left and this as the right and do the substitution. It might work, it may not, but you gotta try. Okay, I'll leave that to you. So we're gonna apply the EQLR, which we have done many times. EQLR. At the same time, we also need to do monotonicity, the rule, because after the equality, usually we don't need this equality anymore, so we can drop it. But that's the only thing we want to drop. So what I will have is I'm gonna get another sequence over here. Let's say over here. Okay, so I'm still gonna get this green not equal to the red, and also this one will be dropped, and this one over here, MLTL, the left hand side, should be replaced by the green, so that should be green. So green equals red. Oh, wrong color. So that should be green equals red, and then everything else should stay the same. We don't drop them. ILTL equals green, and turnstile 1 equals 0. Again, we're replacing every occurrence of MLTL over here by green. That's why you see green equals red. And what else? And the next one to do is, you can see we got some negation over here in the hypothesis. That one matches the not L inference rule that we just learned this week, right? That's something we can do. And more precisely, you can see this is the negation, and we also got some go. According to the not L rule, let's see. That one there really corresponds to contrapositive. So if we got some negation, negative hypothesis, and some go, we can definitely do the negation of the go and let it serve as a hypothesis instead. And also the negation of the negative hypothesis, it will be double negated, so that'll be just P over here, and it becomes the go. Okay? That's something we spoke about earlier. I'm just reiterating the points. So what we will apply is, it's going to be not L. Not L. And what would that be? What's going to happen is take the negation of this and put it as the go instead. Take the negation of this and put it as a hypothesis instead. That's what we're going to do. And these two hypotheses will stay the same. These two, right? Let's put them down first. Okay, so again, let me have this one over here. Okay. So let me copy these two existing hypotheses. Green. Oh, let me write better. Equals red. And also ILTL equals green. Okay, and 1 equals 0 used to be the goal. Take the negation of that, which would be 1 not equal to 0. Agree? And then turnstile, and this negative hypothesis is going to become the goal. But take the negation of that, which would be green equals red. And do you think we're done? Well, is there any rule that we can apply to say now this sequence is provable? You can see green equals red. We can find green equals red, right? So then in that case, we're done. We got the hypothesis rule can be applied, which was not really listed here, but since we have done this for many times, so this one should be okay. Right? You can see we have the hypothesis, one of the hypotheses matching the goal. In that case, it will be proved automatically. Right? So that's about the first case. What about the bottom case? We'll do something kind of similar. Okay. Again, you got two equalities over here, and of course there are two possible ways to really apply the EQLR. But let me apply one of them. You can try the other one as the exercise. What I will do is I'm going to say ILTL is the left hand side, and the red over here is the right hand side. Do we have any other occurrences for the left hand side? Indeed, ILTL over here. Okay, so we're going to do something very similar as before. We're going to say EQLR, and then use the monotonicity to drop this equality over here afterwards. Okay, let's see what's going to happen. And of course, these two hypotheses remain the same. Let's now copy them. So let me have a box over here. Right, so green not equal to red. MLTL equals green. And this one here will be dropped based on monotonicity. And this one over here, the left hand side is going to be replaced by right hand side. So we got red equals green. Red equals green. And turnstile 1 equals 0. Right? And again, we see a very applicable scenario for not L over here because we got negative hypothesis. Right? So we're going to do something very similar as before. This one over here, and this one over here. Take the negation of this, put it in the hypothesis. Take the negation of this and put it as the goal. That's exactly what not L tells us to do. So we're going to say not L over here, and then I'm going to draw the box over here. Okay, what should that be? And we still got these two hypotheses, right? They remain the same. MLTL equals green. Also red equals green. And also 1 not equal to 0, right? And I'm going to put a turnstile over here. I'm just running out of space. And what should be the goal? It should be the negation of this negative hypothesis. That should be green equals red. Green equals red. I should have drawn this box a little bit larger. I can definitely do that. Right? Yeah, it's always good to box everything. So when you do this kind of proof in the exam, for example, you better use a pencil rather than pen, so it gives you more flexibility to actually adjust the layout of the proof. Okay, and do we have a proof now? Indeed, you can see red equals green and green equals red. Of course, you could have just applied another arithmetic ARI to say that we can change the order of the equality, but we don't have to. You can directly say red equals green and green equals red. They're just the same, right? Because of the associativity. Oh, sorry, the commutativity of the equality. Right? So we're going to conclude this case over here by the same rule. What is that? Hypothesis. We see the same hypothesis in the goal. right? It's going to be HYP, HYP, and we are done. All right, it's a very simple proof, but I think the reason I wanted to do this with you is because I haven't done this with you for a long time, and also we are also using some new rule over here, so I think it's nice to really see how exactly to apply it, right? And exercise for you. Even though for the next invariant proof obligation IL out, invariant 2-3, we have kind of the same proof sequence to be discharged that used to fail in the first attempt. However, I can tell you that this proof over here is not exactly identical to what we are doing over here, even though they're very similar. So I would suggest, rather than me wasting your time to really do it together in the video, why don't you try that as an assignment or exercise? Okay, you're gonna see that it's not exactly identical, but you can definitely exercise the rule that we spoke about. Right? So these are the hints for you, and your assignments or little homework will be to complete this proof. Okay, so we are now done with these two proof obligation. This one over here and this one over here. Of course, we failed in the first attempt, and we actually learned from the failed sequence. I think it's a very valuable lesson for you to learn. And then we actually were able to prove after we fixed the invariance. And let's now move on to the next stage, which will be to fix the model even further.